First of all, let us quickly recall the dimension drop conjecture. Let G be a Lie group and gamma be a lattice. In G. And let we use X to denote the homogeneous space G mod gamma. And let mu be the G invariant probability measure on X. For subset f of G, and a non-empty open subset of X, we define E of f, u to be those points in X such that the orbit of X avoids U. The dimension drop conjecture says if F is a sub-semigroup, then either this guy has positive measure or the dimension of it is strictly less than the dimension of X. Here the dimension is the Hausdorff dimension, and here it's a manifold dimension, which is the same as the Hausdorff dimension. And the Kleinbock and Mirzadeh prove that the conjecture holds for the case of special linear groups and diagonal flows, which we will now describe. Now let's talk about this more concretely. Let the Lie group G is a special linear group SL m plus n r, and the gamma be SL m plus n z, and X is still the quotient, the homogeneous space. And set F plus to the point G sub t with G greater or equal to 0, where G sub t is equal to the diagonal matrix. Now there are m terms here and n terms here, so that their product, which is a determinant, is equal to 1, because it should be in the special linear group. And we will also choose a parameter a greater than 0 and consider a subsemigroup Fa plus of Ff plus generated by G sub a. Specifically, this means Fa plus is all those diagonal matrices, T is always a positive integer. So next notion is called the unstable horospherical subgroup with respect to F plus. This is denoted by H, consisting of the matrices where H sub x is the upper triangular matrix with this upper triangular term be an arbitrary n by n matrix. Now we compute the following conjugation. So GT HS G negative T. This by definition is ENT IM E negative MT IN 0 0. So in the middle you have this guy, and on the right you have, and this is equal to, let's see, ENTIM ENTS E negative MT IN times ENTIM EMTIN, which is equal to the E raised to the power m plus nt times the matrix X. So from here we can see that the conjugation map H sub s mapped to the conjugation corresponds to a dilation of S by e to the m plus nth power, e to the m plus nt power, as given here. Now we are going to introduce three notations: an open subset U of X and the parameter r greater than 0. We denote by sigma sub r of U, the so-called inner R core of U. This is a subset of points where the distance from that point to the complement of U is greater than R. And we can draw a picture. So if this is U, this is UC. And the R core will be the part whose distance to the complement of U is greater than R. And we can choose this metric to be right invariant. And we should note that it's an open subset of U. As a measure of this, is close to that of u if r is close to 0, which implies that the following quantity denoted theta sub u, which is defined to be the supremum of those theta between 0 and 1, such that the measure of this guy is greater or equal to the half of the measure of u. This quantity is always positive if u is non-empty. And finally, for a closed subset S of X and the positive number R, we denote by delta RS the R neighborhood of S, which is the partial RS, the points in X where the distance between X and S is less than R. Now we are ready to state their main result. This is the theorem of Kleinbock and Mirzadeh 20. So there exist positive constants. There are 1, 2, 3, 4, 5 constants. C are 1, P1, P2, P3, such that for any a greater than 0, and for any open subset u of X, one has the codimension of this guy is bounded below by a constant multiple of u, the measure of u over the log of 1 over RUA, where this RUA is equal to the minimum of the 4 terms, and in particular this implies the dimension drop conjecture. If U is non-empty, then we have the dimension of this guy strictly less than the full dimension. Now let me briefly talk about their idea of the proof. It's hard to study the codimension of this directly. First, we will instead study the codimension of this guy intersection the orbits hx. Consider the intersection E fa plus u and the orbits. Remember, this H is the unstable holospherical group defining here. So, specifically, we want to prove the following. That there exists still those constants C, R1, P1, P2, P3, and for any positive number A and any x in the homogeneous space and any open subset U of x, one has the following inequality. The codimension of those points in H, those group elements in H, where H dot x is in this E set, is greater than the constant multiple of this, the same term on the right hand side above. And this RUA is the same as above. The key step in proving this theorem will be to break down this estimate in two parts. And this is given by the following key lemma. So lemma says there exists a nested family of compact subsets Q sub t, where t is positive, of x with the following properties. First of all, there exists C1 greater or equal to 0, C1 greater or equal to 1, such that for all t positive satisfying the e to the negative 2t is less than or equal to 1 over 8, and all x in the homogeneous space, and for all integers greater or equal to 2, the following set, let me use another color, S KTX, defined to be those elements in H such that the G sub an arithmetic progression dot H dot X is in the complement of Qt. This means an arithmetic progression parameterized diagonal action of hx will be outside of the compact set. And this set satisfies the codimension greater or equal to this guy. So this is one part, and then the other part states the following. There exists p greater or equal to m plus n. The parameter r2 between 0 and 1 over 16 times square root of the mn, and the c2 between 0 and 1, and some constants b0, b, k1, k2, c3, lambda greater than 0, such that for all t in the a multiple of natural numbers satisfying the same inequality here, and all k, which is a natural number at least 2, and all r satisfying the following inequality. The r is greater than this power of e, and less than the minimum of those two guys, and all theta between 4 times r and 1 over 2 times mn, and all x in r in capital X, and for all open subsets U of X, we have the codimension of all the h in H minus the subset defined here, where hx is in E of fa plus, comma u, is greater or equal to the k1 mu sigma sub square root of mn theta of u minus, there are two terms, so t divided by 4, and the whole thing divided by kt times m plus n. And now, once you establish this lemma, you have two estimates, one estimate here and one estimate here, and you combine those two to get this theorem we want.